Now let's apply our newfound knowledge of arc length and its formula to an actual example or two. So we have a value, well, let me show you. When t is equal to 0, so let me put r of 0, it would be, well, the 3 times the cosine of 0, which is 3, 0, and 0. And then r of 2 pi would also be 3 and 0, but then 2 pi. So it's growing in the z direction. So you start here at 3, 0, 0, because this is the x-axis, of course, and you're spiraling up. Let's do it with this curve. You're spiraling up, and you're landing above where you were, but now there's a distance of 2 pi. So this is 3, 0, 2 pi, and then this is 3, 0, 0. So this was time t equals 2 pi, and this is time t equals 0. It's a parametric equation, of course, because it's a vector valued function. So the vectors are defined by the parameter t, and it moves over time. Okay, so then what's the derivative of this? Because when you look at the formula for arc length, we're going to need to know r prime. So we might as well go figure that out. The derivative of cosine is negative sine. The derivative of sine is cosine. And the derivative of t is 1. Okay, so now let's look at the arc length formula. The arc length formula is the integral from a to b of the magnitude of r prime of t dt, which would be equal to the integral from, well, your t values are 0 and 2 pi, and then we're going to take the magnitude. So we'll take the square root of, and have to have a dt at the end here, and then we will take those values from our derivative and square them. Luckily, that last one's a number, so I knew that. So it'll be negative 3 sine of t, 3 cosine of t, and 1. All right, well, let's think about this for just a second. This is 9 sine squared t plus 9 cosine squared t, which is the Pythagorean identity. That's 9. Okay, so we actually have our arc length is the integral from 0 to 2 pi of the square root of 10, because 9 plus 1 is 10, dt. Because I have a 1 right here and a 9 right here, and together they make 10. Okay, well, this is an integral everybody can do, because that's the square root of 10t from 0 to 2 pi, which is 2 pi square root of 10. Now, I didn't give units for this problem, so let me go up here. Let's say we assume meters. I'll actually put that in for future. So if we assume meters are our units for x and y, then this would be meters, because arc length, of course, is a distance. Right? So if x, y, and z are in meters, then so would our arc length be. All right, next. Well, if we look at this problem here, there's actually a typo here, because this is our position vector. So we want to find the length of this curve. If you look here, if I put t equals 0 in, I would get 0, 0, 4. So this is a typo. It should say 4. I'll fix that for future. So this is t equals 0 right here, that value. This, okay, I need to figure out what this could be. So I need t squared to be equal to 9, t squared, 9. So that means t is equal to 3. It also works with t to the third equals 27, right? 3 to the third is 27, so that also works, right? So this is why that is the case. Okay, so I'm going to go from t equals 0 to t equals 3. There's my limits of integration. Now for my arc length. I do still need the derivative of this, so I need r prime of t. Well, the derivative of t squared is 2t. Derivative of t cubed is 3t squared. The derivative of 4t is 0 because that's a constant. All right, so then arc length is the integral from a to b of the magnitude of r prime of t dt. We figured out the 0 and the 3. That's where those two pieces go. And then the magnitude is a big square root. So we're going to take a square root, 2t squared, sorry, my pen got in the way, plus 3t squared plus 0 squared, which we don't have to write, but I'll just put it in there for fun. And that closes that square root off. Okay, well, this is the integral from 0 to 3 of, actually, I'll keep my blue color there, 0 to 3 of 4t squared plus 9t to the 4th dt. And that is not something we are going to do by hand. We are going to have Maple do it. So let me pull up Maple really quickly, which I actually had earlier. There's the earlier Pringle curve, right, the elliptic paraboloid. And then here's this curve that I just drew for example 1. You can see it starts at 0 and goes to 2 pi. There's the integral there, so you can see the answer. Oh, and I actually didn't write this down. Oh, I did in feet, but instead of meters. Either way, it should have been 19.869 for that first example. And then if you look here at that one, here, let me make this larger so you can see it. I go like that. So right here you can see when I run the integral of the square root, that's the answer I got. And then I didn't like that, so I wanted it to tell me a decimal approximation. So I did the at 10 digits, and it gives me 17.28. And I guess I'll just leave it in feet on this one. So I'll make this feet. Assume x and y are in feet. Make that go away. So let me just kind of throw in that here. Assume x, y, z are in feet. It wasn't in there. I'll put it in for future. So if they're in feet, then that means that when I do this with Maple and I get approximately 28.7, it would be feet. And as always, when we're using Maple to do an integral like that, we will just denote it that, because the setup is what's important to us, and then the actual integration we would use Maple to do. All right, that's the end of that example. So let's stop there, and then the next example will be in the next video.